This afternoon session. Our first speaker is Fredrik Viklund. He will tell us about scaling limits of loop-based random walk Green's functions.
Thanks a lot, Alan. It was a good choice of chair because, well, your shirt is matching my slides. So it's very fortunate. So thanks a lot. First of all, let me thank Michael and Tom for doing such a great job organizing this week. I think everybody here will agree that this has really been a super nice week with many nice talks and this beautiful dinner yesterday and so on. So thanks for that. And well, second, let me just say before I start that Greg has had of course a huge impact on me as a researcher. I mean, both as an author of all these papers, but also as a collaborator. So it's a real pleasure. I'm really happy to be here to take part in this celebration of the 60th. Okay, so I will actually tell you about two joint projects with Greg, and well, one of them is also joint with Chris Benesch, who's also here, who spoke yesterday, and so the one which is joint with Chris concerns what we call the loop-erased walk Green's function and its convergence towards the SLE2 counterpart. So here the goal will be to try to explain the main ideas of the proofs and what are the techniques that go into the proof and so on and so forth. So okay, so a little bit of this, and then in the second part, which is going to be shorter than the first one, I'll discuss an ongoing work with Greg, which concerns the convergence of loop-erased walk in the natural parameterization. This is, as I said, work in progress, but I'll try to sketch a sort of argument which is being written down. Okay. So when I say the loop-erased walk Green's function, what I really mean, and it's just the short way of talking about the probability that a loop-erased walk uses a given edge inside a simply connected domain. So here's a picture to have in mind. So we have some some simply connected domain like this, D, and let's suppose we take some suitable lattice approximation of this domain. We have two marked boundary points A and B, and then we run loop-erased walk between these two boundary points. Okay, so I'll be more precise later, I mean exactly how to define these things and so on. And then we ask the question, what's the probability that this random self-voiding path runs through or goes through a given edge in the interior. Right? And then if things are good, you might hope that if you renormalize this probability properly, pass to the limit with the mesh size, you get some nice function. Right? Of course, this function should depend on the domain. It should depend on the location of the edge and all the other data of the problem. Right? And this function, if it exists, is what we call the Green's function. So it's really the probabilist's definition of the word, so I mean, it's not the fundamental solution of the Laplacian or something like this. Okay, so to actually do the problem, it turns out to be better or more convenient to instead look at domains living on Z2 and let them grow instead. Right? Okay, so here's a more precise setup. So we consider some subset of Z2. And let's suppose it's finite, okay? And we have two marked boundary edges, A and B, which I drew there. And then there's also a marked interior edge, E, which is this little green guy here. And let's just suppose that it is the edge that connects the point 0 to 1. So by the way, so I will always think about everything as being embedded in the complex plane in the standard way. Right? Okay, and then there's also a sort of special point, W0, a marked point, which is really a vertex on the dual grid of Z2. Let me maybe just so you remember. Okay, so this will be a little bit important later on. And then to this discrete domain, this discrete collection of of lattice points, we associate a complex domain, a Jordan domain, D sub A. We can do this in different ways, but one way to do it is to take the closed squares of side length 1, centered at the vertices, take the union, and then take the interior of what comes out. So this gives you, so the boundary here is drawn in blue. Okay, and then, well, when you have a domain like this, of course, what you want to do is map it to the unit disk, or at least I want to do that. So we have the uniformizing conformal map phi, which takes d sub a onto to the unit disk. We're not going to normalize it in the usual way by sending to 0 to 0 and have the derivative be positive there, but actually we're going to send this marked dual vertex point w naught to 0 and have the derivative be positive there. Okay, so that turns out to be sort of convenient. Okay, and as I said before, eventually we're going to let this domain grow and become large, and the way we measure the size will be through the conformal radius. And by that I mean the conformal radius of the complex domain dA. So it's just the inverse of the derivative of the conformal map, okay, at this point w naught. Okay, and then loop raised walk, I suppose, well, essentially everybody will know the definition, but okay, let me just say it anyway. So we consider a chordal setting here. So we look at a simple random walk started at one of these, let's say the vertex of A, which is sitting outside of the domain, and then we look at a walk which is conditioned to enter the domain, and then it does its thing in here, and then we condition it to exit the domain through B. Okay. And then we erase the loops of this random walk in chronological order, and the output of this algorithm is the loop raised walk. Okay, in the chordal setting. So it's some probability measure on random self-avoiding paths. And then, well, one way of stating the theorem already now is as follows. So suppose we have this picture here, and so we have a loop raised walk in the domain A, running between these two prescribed boundary edges A and B. Then, excuse me, there are constants. There's a constant C naught, strictly between 0 and infinity. There is some positive number u, such that, well, the probability that eta goes through this green edge here, well, satisfies this relation here, right? So it's a constant times, there's a covariant factor, the conformal radius to the power minus 3/4. And then there's an invariant factor, sine cubed, and here theta is pi times the harmonic measure of, let's say, this boundary arc seen from w naught. Right? So this in some sense measures how, I mean, this quantity becomes small if you're close to the boundary. Okay. And then there is this polynomial error term here also. Right? So
C naught and U do not depend on A.
that's right. Yes. Right. Yeah.
So the capital, I mean, the O is uniform with respect to all A's and thetas, or does theta have to be away from?
It's written in this way. But this takes care of the problem with the boundary Poisson curve. That's where it's coming from. Yeah. Okay, so several of you, I'm sure, well, I know, will recognize on the right-hand side the SLE2 Green's function. So how do we define that? Well, we do a similar thing as before. We look at the probability, take a simply connected domain D, let's say dA, before. We run an SLE between the two marked boundary points. We ask what's the probability that the SLE hits a ball radius epsilon in the interior. We normalize this probability and pass to the limit, and the result is some constant times the right hand side here. So of course, this is non-trivial, I mean highly non-trivial to show. I mean this phrase like this was proved recently, I mean quite recently by Greg and Mohammed Rezai. So when I say phrase this way, I mean that we have a Euclidean ball here. So it's slightly easier to do this if you instead measure the distance from Z by a conformal radius. Okay. And I think, so let me just make a comment. So we'll return to this, but this constant C naught here, which is sitting in front of, I mean this is some lattice-dependent constant, but we don't know how to compute it at this point. We will see. We do know it's a product of 3 other constants that we also don't know how to compute. But I think also this constant is not known, right? Yeah. But for the conformal radius version, it's known. Yeah. Okay. Okay. So that's the statement. And of course, this result is part of a story which has been going on for, I guess, 25 years more or less. So I remind you that the exponent we had here, 3/4, is of course closely related to what is called usually the growth exponent, which is the expected number of steps the walk makes in the domain. So it's a sort of discrete measure of fractal dimension. This number was predicted in the physics literature in the early 90s by both simulations and theoretical arguments. And then about 10 years later, Kenyon proved that this was correct. So he computed the correct growth exponent for loop-raised walk. So in the actual estimate, there is a log correction, but the exponent is this. And also found in a slightly different setting involving, not in a general domain, but in a half plane, also found the sort of correct angle dependence, which corresponds to this sine term in our formula. And then Masson, a grad student of Greg's, also computed using different methods the growth exponent using Lawler-Schamm and Werner's convergence result of loop-raised walk towards SLE2 and some SLE computations in order to derive the growth exponent. And then recently, Kenyon and Wilson obtained some exact values for this probability, the probability that loop-raised walk uses an edge. So they looked at the sort of whole plane setting and computed these numbers in the vicinity of the origin. So they call it the loop-raised walk intensity in that paper. And then Greg very recently obtained up to constants estimates of the decay rate of the probability that the walk goes through an edge in sort of special domains, in square domains. And he used some sort of important ideas from Kenyon's work, and as do we. So this is related to what Julien was discussing the other day. So I'll return to this. Okay, so what is the contribution of our result? Well, we obtain really asymptotics. I mean, okay, we don't compute the constant, but we get the asymptotics, and also our result works for general simply connected domains, and this is going to be important later on for this part 2 of the talk, this natural parameterization question. All right. Okay, so the proof of the result has essentially 2 main components. So in the first step, we rewrite the probability we're looking for using essentially combinatorial arguments as a product of quantities that can be expressed in terms of simple random walks. Then in step 2, well, you estimate. So, I mean, in the bulk of the paper, happens at step 2 in some sense, right? But this is, not the most. All these technical estimates are not so suitable, perhaps, to sort of present in a talk like this. So I'll more try to first discuss this part and then try to give you some ideas of what goes into the estimate, what techniques we use, and so on. All right. But let's start looking at step 1, so the combinatorial lemma. Then it turns out that it's convenient. It's not a big. It's more a sort of change of point of view, but it turns out to be good to not really think about loop-raised walk as a probability measure always, but also as a finite measure on self-voiding walks. And so I just remind you that a walk, or I tell you that a walk is a sequence of nearest neighbors on the grid, and the length of the walk is the number of steps it takes. Okay. And then to any such walk on Z2, we associate a number, namely 1/4, to the power the length of the walk, and we can think about this as basically the product of edge weights along the path where all the edge weights are equal, namely 1/4. Okay, so this is just the random walk probability of jumping to one of the neighbors. Okay, that's the walks, and we have the simple random walk measure. Okay, and then what has been discussed in several talks already, we have also loops. So loop is a special kind of walk which starts and ends at the same point. Okay, and this special point where it starts and ends is called a root. Right. So then to loops we associate a loop measure, which is for rooted loops defined as just the random walk measure divided by the length of the loop. And then if we forget about the root, namely just sum these guys over all the rooted loops that under cyclic permutation of the indices, we keep the orientation of the loop. Well, you get the unrooted loop measure. So this was discussed a bit by Wendelin and implicitly by Michael. Okay, so we have walks and we have loops, and we also have loop-raised walks. So the loop-raised measure is defined as, can be defined as follows. So if eta is a self-voiding walk, in the picture we had a few slides ago, then the loop-raised measure of this guy is equal to the random walk measure of the loop of the walk. So it's just the product. It's just 1/4 times to the power the length of eta, and then there is this loop term. So this term, this factor already appeared in Michael's talk yesterday. So not exactly in this form, because he wrote it as a product of Green's functions evaluated in sort of smaller and smaller domains when you successively grow the self-voiding walk. Right. But it can also be written in terms of the loop measure as the exponential of the loop measure of loops staying in A that intersect eta. So this is sort of the loops. This is also related to what Wendelin discussed. This is somehow the loops that get erased in this loop raising procedure. Okay. So notice though that written like this. Okay, so there's also another way of writing this as follows. So if we fix a self-voiding walk eta, then typically, of course, there will be many walks such that if you apply the loop raising algorithm to them, you end up with eta. Okay, so the pre-image of any self-voiding walk under this loop raising map will have many points, right? So so another way of writing the loop raised measure is just to sum the random walk weights over all these guys. Okay. And this, you have to check. So starting from this expression, one easily sees that the total mass of this measure is not 1, but it's rather the probability that the random walk starts using the edge A, runs in the domain big A, and then exits through the edge B. So this could also be called a discrete boundary Poisson kernel. Right. So by the way, when I write, I think this is self-explanatory, but when I write something like this, it of course means that the walk is running in the domain A that we have fixed between these two either boundary points or boundary edges, okay, depending a little bit on context. So with this new notation, we can write the probability we're looking for as follows. So the probability that eta runs through the edge E is just the loop-raised measure of the set of self-voiding walks, with the correct starting and end points that run through the edge E, okay, and then divided by this total mass of the measure. Okay. So this is the expression that we're going to work with, and what one can observe already now is that the guy down here is something that we know pretty well how to estimate. We can express this in terms of the corresponding thing for Brownian motion and so on. So the thing to focus on is this guy now. So okay, so if you have a self-voiding walk that goes through the edge E, either it will go through first by visiting 0 and then 1, or first 1 and then 0. This is sort of clear. So we can split this guy into two terms like that. And well, what we would like is some nice expression for this. Okay, this is a bit vague, but as I said before, really the goal is to have an expression that we can do estimates on. That we can sort of apply some nice techniques to. So then it turns out that it's a little bit easier, or actually a lot easier, to to get a nice expression for the difference of these two. So let's look at that example first, because it will tell us, well, it will help us to do the other case too, right? So if we look at the difference, well, we get an expression. Well, okay, this is the difference, okay, and then we're interested in the loop raised measure of paths doing this minus the loop raised measure of paths doing that. So then, if you look at this formula, either using this loop measure representation or in terms of Green's functions or something like that, well, what you end up with is a formula like this. So if you look at the first term, then this is going to contain, well, one factor, which is the random walk measure of this edge, and then the exponential of the loop random walk loop measure of loops staying in A, but intersecting the edge E. Okay, and then there is this factor here, where we're summing. This is a double sum over random walk weights, where the walks are such that we sum of random walks from A to 0 and from 1 to B, but there is this non-intersection condition, right? So the walk from 1 to B should not intersect the loop ratio of the path of the walk from A to 0. Okay, and then the other term is the same, except the walks are now running from A to 1 and from 0 to B. Okay, and then we take a difference. Okay, so at this point we didn't really do so much. So then the question is this a nice expression or not? Well, it's not so clear how to directly work with this, because we have this non-intersecting condition, which is not so easy to handle. I mean, this factor, however, is quite nice, right? Because it just depends on the domain and on this edge. So this we would have some better hope of working with, right? But then it turns out that there is a sort of combinatorial lemma or observation, which is called often Fomin's identity, which tells you that actually, because we take a difference here, we can just forget about this non-intersecting condition. And that is not hard to see. It just comes from, if you look at these these two sums, if you look at the paths here in this guy that actually do intersect, I mean so such that W2 does intersect the loop ratio of W1, well then you can construct a bijection to see that actually all of these terms will also appear in this sum. So there is a cancellation. Okay. So this sort of formula has, I mean, this I think is well known. I mean, it's a similar formula in work of Kenyon and so on. Okay. But so this is nice, of course, because, well, this expression here can be written only in terms of random walk quantities. However, we're not really interested in the difference of these two. We're interested in the sum, right? So what can we do in order to proceed? So then a solution is to introduce to introduce a puncture in DA, and in this way introduce signed weights, right? So this is related to what Julien was talking about, and also work of Kenyon and so on. So we're going to do the following. So here is our domain. We're just going to draw a straight slit like this, which is parallel to the imaginary axis, until we hit the boundary of D sub A from W0. And this will be our branch cut beta. And then using that, we're going to define a signed edge weight. So some of the edges of Z2 will intersect this curve beta. And for these edges, we define Q of E to be minus 1/4, so minus the random walk weight. And for all the other edges that don't intersect beta, well, we get the weight plus 1/4. It's just a random walk weight. And then, and this is one of the benefits of sort of not thinking about loop raised walk really as a probability measure, but rather as just as a finite measure. one then realizes that actually all of the definitions I gave before, the loop measure, the random walk measure, and the loop raised measure, all of them make sense also for this signed weight. We just replace the p by the q. Okay. And the formulas also hold. So for instance, we can write this, okay, I gave this as a definition, but the loop raised measure satisfies this sort of thing, and is also equal to the sum of the q weights of the sort of random walks whose loop ratio give you eta and so on. Okay. Okay. So what's the point of all this now? But then there is okay. Let me just say this. So another way of thinking about this is the following. Which is a little bit useful later on. So I mean, geometrically, when we introduce this puncture and branch cut, we can think about this as we are, making two copies of the domain, putting them and gluing them along beta, so we get a two cover of the domain. And then what Q allows us to do is to basically keep track of when we go between the two different sheets. Okay, okay, and then a nice observation is the following. So there is now a way to relate the. Remember, this is this was this loop term that appeared in the loop raised Q measure, the signed loop raised measure, and this is the regular loop term. So the exponential of the usual random walk loop measure of loops staying in A intersecting eta. And this is the same thing, except we define the loop measure in terms of Q instead. Okay, so we have this extra sign appearing. So it turns out you can relate these two quantities according to the following formula. And I mean, the reason for this is simply that if you have a loop that intersects eta such that you sort of pick up a minus sign when you go around the loop, well then that loop has odd winding number about W naught. And I mean, what is nice with this formula is that this factor that relates these two quantities doesn't depend on eta. It just depends on the domain and W naught. Okay. So then, well, if you label the edges properly, actually what this tells you is that the loop raised the sum that we're interested in can actually be written as a difference, but between these loop raised Q measures, these signed loop raised measures, times this factor, which doesn't depend on eta, but just depends on the domain. So the exponential of 2 times the random walk loop measure of loops of odd winding number about W naught. But this is good news, right? Because here is a difference of loop raised quantity, so we can apply this Fomin style argument again to this quantity, right? And the end result, after a little bit of fiddling, is the following formula. So the probability we're looking for can be written as 1/4 times the signed loop measure of loops staying in A intersecting the edge E. Okay, so that's a factor which just depends on the domain. And then this odd winding number term, also a loop measure term. And then there is this last determinantal type factor where I'm writing HQ. Okay, so I didn't write this. So K here is the domain A, the discrete domain A minus the edge E. So these can be thought of as signed discrete boundary Poisson kernels, but using this sign measure. Okay, and then we have this flipping of arguments here. Okay, so this is actually okay. So then the observation again then is that everything on the right is something which can be phrased essentially as random walk quantities. So if you allow this point of view that you go to this 2 cover instead, then we can really think of it as random walk, but on this 2 cover. Or if you will just signed random walk quantities. And so this is the formula we're looking for. And then the question, after knowing this, is what happens when the conformal radius goes to infinity. Right? So this is somehow the end of step 1 in this sort of combinatorial argument. And so now for 30 minutes I will just do estimates. No. So we need to prove the result, we need to really understand what are the fine asymptotics of each of these quantities. Okay, so I will not discuss all of the terms, but focus actually on the last one. But let me say something about the first two. Okay, so by the way, first of all, so this sort of formula was already used in not in exactly the same form maybe, but was already used in Greg's previous paper. And then also this sort of term appeared. So I mean, you doing a coupling argument, it's not so hard to check that as the conformal radius of A grows, this guy converges to a finite non-zero constant. Okay, so I won't discuss this so much. There's a lot of cancellation going because you have this signed weight, and you're starting very close to the branch cut, to the puncture. And the second factor, well, that requires quite a bit of work. So this was also treated in Greg's 2013 paper, but there he did not obtain as fine asymptotics, and also the argument there was essentially only worked for special domains. So one has to work a bit more here in order to get the asymptotics up to this additive constant here. And the method we use is essentially by comparing the random walk loop measure with the scaling limit of the random walk measure, which is the conformally invariant Brownian loop measure, which was also mentioned in several talks. And so, one can basically couple the Brownian paths and the random walk paths, and in such a way that they are close with high probability. So then, at least if you're away from the puncture, well, then you will know that these paths have the same winding numbers. So you can make a comparison in that way. However, if you're close to the puncture, you have to work a bit more in order to get what you want. So one thing, though, I want to mention, this is a computation that appears in Greg's 2013 paper, that this 1/8 here is the same 1/8 as in this formula. This comes from summing boundary Poisson kernels, less in the half plane over every second period. Okay. But this requires a bit of work. But the main sort of technical issue, somehow the main work in some sense, is in handling the last guy here. Right? So let's have a look at this one. So first of all, if I remind you what is the definition. So this is simply the sum over the Q random walk weights, where we sum over paths staying in K, except for the first step. The paths are running from 0 to an edge, and exit through the edge A. Okay, so it's a bit nicer if you normalize this probability. So we're just going to this quantity. So we're going to divide it by simply just the probability that a random walk starts here and exits the domain through this point. So just the discrete harmonic measure of the edge A. Okay, so if you take that point of view, so that's what I mean by this quantity here. So if you take that point of view, well, then this guy right here can be written as an expected value, where the probability law is that of a random walk starting at 0 here, but conditioned to exit the domain through the edge A. Okay, and what is the random variable we take the expectation of? Well, first it's just the indicator that, except for the first step, it stays in K. Okay, so it doesn't revisit this edge before it exits. And then Q gives you +1 if the walk crosses beta an even number of times, right? Because then the q weight of the path will be equal to p, because if it picks up minus signs, it will be an even number of them, right? So they will cancel, or they will multiply to a +1. And q, however, gives you -1 if it crosses beta an odd number of times. Or, if you wish, you can think about this from the point of view of these two covers. So if we start, let's say we start on the top sheet, then we get +1 if it also exits on the top sheet, and -1 if it exits on the bottom sheet, right? So the fiber or pre-image of A has two edges in this two cover. Okay. So I should also maybe say that so in the actual estimates, it turns out that it's a little bit more convenient to use a different branch cut beta than this particular one we use here, but I mean the idea is essentially the same. Okay, so you have this thing which we can think about as a sort of random walk expectation, okay, so we know that, well, random walks converge to Brownian motion and so on. So I mean, probably this quantity when A becomes large is related to some analogous quantity for Brownian motion. Of course, to count the number of times the Brownian motion intersects beta doesn't make so much sense, but this point of view does make sense, right? If you have a continuous path. So I mean, given this intuitive reasoning, it's actually possible to guess what the scaling limit should be. So let me just briefly explain this. So here now I look at a little bit simplified geometric situation. So I changed the branch cut here to be this radius here on the real axis. Okay, so then suppose we start a Brownian H process, a Brownian motion conditioned to exit the unit disk at A from Z. Then well, one can observe first that, and then we look at the expected value of, well, okay, more or less the number of times it intersects beta, or this plus minus variable depending on, you know, if we exit on the same sheet that we started or on the other sheet. Right? Well, so simply for symmetry reasons, if you start the guy on this antipodal radius alpha here, well, the expectation is 0, because it's as likely to go in this direction as in the other direction. Okay. But then that actually tells you that that essentially identifies what you would guess the scaling limit to be. Simply because if you start sort of outside of this little piece here, well, then the only way for you to pick up the minus sign is if you go around like that. But then you will intersect alpha. So actually the value here should be equal to +1 times the probability that you that you don't intersect the antipolar radius alpha before exiting. However, if you start in here, inside this little cake piece, then you have the opposite situation. So the only way for you, I mean, either you go through alpha, and then by the Markov property you pick up 0, or you go in the other direction, but then you necessarily pick up a minus sign. So with this sort of heuristic argument, we would expect that the expectation actually equals the plus minus the probability that the H process started inside the domain avoids alpha. And this sort of probability can just be computed directly. So here I didn't say this, but these are simply Poisson kernels for the slit disk, and this is the Poisson kernel for the disk. Okay, so you can guess this, and indeed we prove that the limiting behavior is given by this function. So plus minus times this guy. And remember that the conformal map phi didn't send 0 to 0, but rather this W naught to 0. So this point is going to be slightly away from 0 here. Okay, and then one can compute the following asymptotics, right? I mean, part of the issue here is that we start very close to the puncture W naught, so you have to you know, we can't apply these coupling arguments that I sort of alluded to a little bit before when I discussed the convergence of the random walk. I mean, this the random walk measure of the loops of odd winding numbers. So one has to do something. You know, there are two different steps in the proof. So first, you somehow have to get away from the vicinity of the puncture, but then once you get away at a sort of macroscopic distance, one can apply these coupling techniques that we like to use. Okay, so at the end of the day, you work this out. Well, you prove the theorem, right? And as you maybe or can see from this formula, the various exponents have I mean, the two exponents have different contributions, right? So we get this 1/4 is coming from this loops of odd winding number factor, and then we get the squared. I mean, r to the -1 is coming from this, what I discussed before, right? And there's also one of the signs is coming from there, and then this sign squared is coming from, well, I didn't say this at all, but one has to do something with this guy too, and express this in terms of random walk hitting probability starting from the origin and going out. So that gives you a sign squared there. Okay. And so the constant, you know, it's both involves well, the limit of this guy, which is a constant, but also this constant term in the asymptotics for this loop measure, but also there is a constant coming from this guy. So some questions that one might pose is it possible to compute this lattice dependent constant? I mean, perhaps using other sort of related methods like discrete complex analysis or dimer methods and so on. And that would be very interesting to see. And well, you can also try to employ a similar argument to do a sort of 2-point function, and you know, with maybe complex weights and so on. All right. Okay, so this finishes the discussion of sort of project 1. Now, for the last 10 or so minutes, let me change gears a little bit and discuss this ongoing work with Greg. So, okay, so I mean, the main motivation for doing the work, proving this result, is that we are interested in trying to prove that loop raised walk converges to SLE2 in the natural parameterization. And well, we still haven't quite finished, but okay. For those of you who were here for the first workshop in January, I mean, somehow this result was mentioned in 2 talks, neither of which was given by me or Greg. So I thought it would be good to at least say something. Okay, so what I will give you is a sketch of a proof which is still lacking some written details, right? But we're quite confident that it will work. Okay, so just first let me say that I mean, for this problem it's okay. It's a little bit better or more convenient to change picture and instead now fix some nice domain D and then let this lattice domain be some nice approximation of D, right? With some marked boundary points A and B or marked boundary edges perhaps. Okay. And then the statement, I mean, one version of this sort of vague statement is the following. So there exists a coupling of loop raised walk and SLE2, so we can define them on the same probability space. And the paths are parameterized by capacity, and in this coupling with large probability, well, the curves are uniformly close. Okay, but this we already know. I mean, this is the sort of standard, well, this is the kind of convergence result that is already known, right? That loop raised walk converges to SLE2 when the paths are parameterized by capacity. This parameterization, which is you get from the Loebner equation. But then the additional thing you would like to know is that at every capacity time, the normalized number of steps of the loop raised walk and the Minkowski content, or the natural time of the corresponding piece of the SLE, are close. Okay. And this is sort of the goal of this little sketch I will give you. And what I want to do really is to emphasize how the previous theorem is really a sort of critical step in the proof of in the goal proof of this statement. All right. So okay, so how is it related to the convergence result? Well, we're going to use it in two different forms, right? But one consequence is the following. So if we look at the loop-raised walk in one of these pictures, and we let t be the total number of steps the walk makes, then the expected number of steps, if you renormalize it properly, so here C naught is the sort of correct constant that we obtained from our theorem, converges to the integral. Sorry, n was the 1 over n is the mesh size. Yeah, thank you. So we see this 5/4 appearing, and so this guy converges to the integral of the SLE2 Green's function over the domain D plus some error term, which hopefully one can have as a sort of polynomial in terms of the mesh size. Certainly, our result gives the bulk contributions. If you restrict attention to points which are inside the domain, then you know, one gets this. But there's also contribution from the boundary and from points near A and B. Right? So this one has to handle. Okay. So then the strategy is as follows. So the first step is to basically reprove the result of previous result of Lawler-Shammer-Werner and Dapeng, but namely to couple loop-raised walk and SLE2 in such a way that the paths are closed when they're parameterized by capacity. And here one can use this martingale observable technique that Julien mentioned, but we can actually use our loop-raised walk Green's function as a martingale observable to get a sort of new proof of this. Right? So what you get from this is that the driving terms converge, but then you need some additional arguments in order to say that some regularity equicontinuity estimates in order to say that the paths are actually close when parameterized by capacity. Okay. But this we know how to do. And then one introduces a martingale, which is of the same type that was used in the first existence proof of natural parameterization by Greg and Scott. So, namely, so you remember that T was the total number of steps the walk makes in the domain. Okay, so then we look at the conditional expectation of this random variable, where we grow or sort of grow the loop-raised walk in mesoscopic chunks. So we don't grow it really step by step, but in these sort of intermediate scale chunks. Right? So that's what I meant, mesoscopic capacity increments of the path. Okay, so this martingale will have two parts. So one is just the number of steps you've taken so far, and then the expected number of steps in the complement of the curve. Okay, so this guy is just the sum over these loop-raised walk Green's functions in the sort of slit domain, which is slit by the curve. Okay. And then there is a corresponding SLE martingale, where this is the area integral over the SLE2 Green's function in the complement of the curve, and this is the natural time of the guy, run up to capacity t. Okay. Okay. So then, if we renormalize this guy properly, well, basically by in the correct places, dividing by the proper constant times n to the 5/4, and if we make sure that the paths are run up to the same capacity, we actually get a nice martingale by taking the difference, and this will be a martingale in the coupling, so it depends on the both two other filtrations, right? And then this difference martingale will have two parts. So the first one is a difference of these integrals of Green's functions. So for well, this guy is the renormalized sum over all the discrete Green's functions over the complement of the curve, and that's the corresponding guy for for the SLE2. Okay, and then the other part is simply the difference of the normalized lengths. So the goal of the whole the goal is to prove that this guy is small, uniformly small with large probability. Okay, and then you have to think a bit, but I mean, there is a nice argument which uses the some L2 maximal principle, which the output of which is that the key step is really to basically we get the control we need by making sure that this guy is small, and that has to do with well, one can control the increments of this guy and okay. So the key step really is to use our convergence result in order to make sure that this difference of the super martingales is small. You remember that that's exactly given by the this integral of the discrete Green's function in the complement of the curve minus the integral of the SLE2 Green's function in the complement of the curve. Okay, so we know that these are close, at least in the bulk. But the catch is that that we can't just apply this for every point in the slit domains, only for sort of good points in the sense that they are somehow sufficiently far away from the boundary and they're not sort of cut off by the path in some funny way. So in order to make sure that the paths don't create these sort of bad domains which force the path, the sort of continuation of the curve to spend a lot of time in points at which we can't apply the estimates, we need to do quite a bit of regularity estimates. So for instance, the paths should not be allowed to create these sort of bottleneck domains and these sort of spiral domains and so on. And one also needs to make sure that the solutions to the Löwner equation corresponding to the two driving terms that we know are close are also sort of close in a quantifiable way. And then one also needs some sort of L2 estimates for the maximal number of steps in both. And so there is still some work to be done, but we expect or maybe hope details to be in place soon. Okay, so just to summarize, the main result was that the loop-raised walk Green's function converges to the SLE2 counterpart if you renormalize it properly. And the strategy of the proof was to view loop-raised walk as a finite measure in terms of random walk measure and loop measure and so on. Then there was this combinatorial argument which used ideas from work by Kenyon. So we used these signed weights which allowed us to express the probability we were looking for in terms of these signed random walk probabilities or signed random walk quantities. And then in order to do the estimates, we mostly used coupling techniques, so these strong approximation results, just comparing random walk quantities with Brownian motion quantities. And then this result is a key step in the strategy that we are currently pursuing in order to prove convergence in natural parameterization. And so this first step here was to couple the paths, and we can use the loop-raised walk Green's function as a martingale observable. And then the idea was to introduce these natural time martingales, take a difference, and then it turns out to be essentially enough to understand the difference between these two super martingale parts. And for that, one uses our convergence result. Okay, so thank you very much, and happy birthday to Greg.
Okay, thanks for a beautiful talk, Fredrik. Do we have any questions or comments for Fredrik? So perhaps the question is this lattice-dependent constants. Do you have any guesses for
No. Do you, Greg? No.
Number 3 could probably be done with the things Rick does. Number 1 has a chance, and I have absolutely no idea for number 2 of the product. So
what are these? 1, 2, 3.
The one for the HQ, the Poisson kernel's HQ, that has to do with the probability of avoiding a half line. That one might be doable. But the one for the number of loops of odd winding number, the first, it's basically, it's the number of loops of odd winding number for small numbers. It's the, can you do that?
David and I know how to do that.
All right.
We should check with you afterwards. We did some calculations.
related to this particular thing?
Well, maybe they know how to calculate.
Not right offhand.
Yeah, our techniques give no approach to it.
Further questions? Well, in that case, let's thank Fredrik again.